Merhaba Seda hocam. Burada mısınız?
Şimdi sesim geliyor mu hocam?
Geliyor hocam.
O zaman az önce gelmiyordu sanıyorum. Kendi
Evet.
kendime konuştum. Tamam.
Başlayabilirsiniz hocam.
Teşekkür
Hazır.
ederim. Çok sağ olun. Değerli hocalarım, değerli öğrencilerimiz merhabalar, günaydın. Ben o zaman birinci oturum için Yasmin Kehail tarafından sunulacak olan Physiologic Based Intelligent Treadmill Speed Control for Cardiopulmonary Rehabilitation başlıklı sunuma Yasmin Kehail'i davet ediyorum.
Merhaba hocam, buradayım.
Merhabalar. Ben
Benim ekranımı
size bırakıyorum.
paylaşabilirim ben şu an değil mi?
Evet evet, ben sesi kapatıp size bırakıyorum.
Tamam, teşekkürler hocam. Ee, Merhaba herkes. Ben Yasmin Kehail, Filistinliyim. 9 Eylül'de yüksek lisans yapıyorum. Aslında ben mekatronik mühendisiyim. Aynı alanda yüksek lisansla devam ediyorum. Ee, Bugün yaptığım proje Physiologic Based Intelligent Treadmill Speed Control for Cardiopulmonary Rehabilitation. Aslında şöyle ben konudan başlayayım dedim anlatmak. Ve İngilizce'de benim için daha rahat olacağı için İngilizce'de anlatacağım. Kusura bakmayın. Um, by intelligent here, I mean that the machine will be able to adjust its speed based on the patient's condition safely without the supervising of a physiotherapist. But heart and lung diseases are very widely. So I will start with explaining the type of patients who I did my study on. Well, the patient who will be able to use our machine or our code uh, should be the patients who undergone open heart surgery in which one of the heart valves was replaced. And exactly one, since there's another types of operations where more than one of the heart valves will get replaced. In these cases, using a smart machine as a rehabilitation process will be risky, high riskly. So just one heart valve replacement yapan hastalar için daha uygun olur. İki, patients who do not suffer from any other diseases or complications. Aynı şey dediğim gibi bu yani bizim riskimiz arttırdığı için e, complication'siz bir şekilde o ameliyat geçirdiği olması gerekiyor. Üç, patients in the third stage of physical therapy. Dört, patients aged between 20 and 50 years. Şu an o iki nokta şöyle anlatayım. For patients who had undergone open heart surgeries, we have three stages of physiotherapy. The first one, in the first week after the surgery. The second stage, between the week 6 and 12 after the surgery. The third one, between the third and the sixth month after the surgery. The first two stages has high risk and it should be inside the hospital where physiotherapist and the cardiologist watching the patient. So we choose the third stage since it's more safer and more suitable to use a smart machine with the patient. The fourth point I will explain later. It will be more understandable. Well, now the differences between our smart machine and the normal smart machines in the market. The smart treadmills in the market are designed for general fitness and include features like heart rate monitoring, preset workout programs, and app connectivity. While our smart treadmills, specifically designed for rehabilitation, adjust speed based on patient-specific data, ensuring a safe and personalized recovery. And as we will see later, it will work especially on the data that the patient gives it to the machine, not a general data, not a generalized something. How does it exactly work? The machine takes the patient's input values for age, body mass index or body mass indicator, BMI, and compares them with their heart rate, which is measured using the machine's built-in sensors. So using this code will not require any other mechanical changes on the treadmill machine. Based on the analysis of this data, it determines the appropriate speed at which the treadmill should operate. And the table on the right shows that the body mass indicator, I divided it into underweight, normal, overweight, and obese. I don't know if you can see my mouse. For example, if a patient who is underweight and he's young with low blood pressure, the machine should work with speed fast. While if his heartbeat is normal, so the machine should work in a speed named very fast. Well, this names based on what? Based on this thing. In fuzzy systems, we usually put numbers and classify the names that we normally use. For example, body mass indicators divided to underweight. When we look at a person, we can just judge him like if he's underweight, normal weight, a little bit overweight, obese. This is what we did here. The classification of body mass indicator has been taken from World Health Organization. And this is why we just took the ages between 20 and 50, since children's has totally different way to calculate and to classify the body mass indicator. Not to go in there, we just took the ages between 20 and 50. About age, young people are people between 20 and 35, adults between 25 and 45, old people between 35 and 50. Well, these ages actually, it might, a person between 20 and 35, for us, he's not or her not young, but for the machine and for rehabilitation processes, it might be young. It might be indeed, it is young. Like his body and his heart can appear much more hard, stressful exercises. Heartbeat low between 60 and 80, normal between 70 and 110, high between 90 and 100. Here we might see a little bit differences. Actually, I don't know how right could it be theoretically, but the overlapping here, the great overlapping here is needed actually because the heartbeat is the main factor affected the speed of the machine and the main factor that affected the health of the patient. So I don't want any harsh or any sudden speed differences. Like I don't want the speed to rise up from 80 kilometers per hour to 5 kilometers per hour. That's why I did this huge overlapping. The speed will vary between 0 and 5. 0 and 1 kilometer per hour represents the very slow, 0.5 to 2.5, moderate between 1.5 to 3.5, fast between 2.5 to 4.5, very fast between 4 to 5 kilometers per hour. Again, we should say that these values have been specifically defined for this machine and for the purpose of rehabilitation. This does not mean that they represent a generally correct classification. The speeds has been said to be firstly safe for the cardiac patients. That's why it might seem slow for the normal person. Patients in the third stage of physiotherapy can use the treadmill in an average 3 to 4 kilometers per hour. That's why we will see it later. The RLIC of the exercise should be, and the speeds should be mostly inside the range between 3 and 4 kilometers per hour. Well, here we can see the input membership functions for the fuzzy system. The first one, body mass indicator. The second one is age. The third one, heart rate function. And looking at the heart rate function, as I said, the huge overlaps. Actually, we can see it here in the figure. The right side of the normal draft. I don't want to be sharp. I just want it to be as smooth as possible. That's why we did that overlap. Completely for health related reasons. The output, as you can see, I will not spend much more time here. Well, now after we named this and after we have the output, we have to translate the output to a numerical value. So we have so many options as a differentiation methods. The first one is centroid, center of area, calculates the center of the gravity of the output. The other one, LOM, or the largest of maximum, picks the largest value where the output membership function reaches its maximum. The other one works exactly the opposite. It chooses the smallest value where the output membership function reaches its maximum. The fourth one, mean of maximum, it takes the average between largest of maximum and the smallest of maximum. For example, let's take a fixed body mass indicator, age and heart rate. For body mass indicator 24, age 45, heart rate 65. The smallest of maximum will choose the lowest peak value, and let's say it's 3.2. The largest of maximum will choose the highest peak value, which let's say it's 3.8. The mean of maximum will take the average between them. So the output, the numerical output will be 3.5, while the centroid will integrate all the entire output area and give us a little more like humanitary number. It will be something like 3.1, 3.2. Here, there's some examples I wanted to show. I took a fixed body mass indicator and fixed age. The number on the left is the body mass indicator. Well, 24 represents a mostly normal weight patient, not overweight, not underweight, normal. We can say that. Age 45, since we're talking about patients between 20 and aged between 20 and 50. So 45, you can consider as old person. And here I want to show how the speeds will change while the patient's heart rate change. Well, starting from 60, it indicates slow heartbeat, which means even fit patient, or he didn't start exercising yet. Therefore, it's appropriate to start at a low speed to avoid a sudden increase in heartbeat. As the heartbeat approaches 95, the patient may begin to enter a risky zone, particularly given their age, so the speed should be reduced accordingly. And here, looking to the diffosification methods, we can say that most of the numbers, the numerical values are close to each other. But since we're dealing with a medical application, personally, I prefer to choose the minimum numbers. So the patient can just spend 2 or 3 minutes more exercising, not to accept a high risk. I can just make the time of the exercising much more. So I chose the centroid method. Why? It made the rule aggregation more nuanced, human-like, and medically safer, which make it perfect for
Son bir dakika diyelim. Yasmin Kehail, son bir dakika.
Tamam. Syndroid seçtik. Bu sebepler için ona girmeyeceğim. Dediğim değerler doğru olduğunu nasıl kanıtladım? İki metot kullandım. Birincisi Zohman, Young ve Katus. Third of them did a study. In this study, they described a protocol. In this protocol, they applied a test using Treadmill for 40,000 patients. Presents normative data on oxygen consumption, age, gender, fitness, level, familiarity with the procedure, and the clinical stages. Although there were not enough data for real patients in the study, but it was useful to make a guess about how much can each patient appear this method. The other one, expert opinion, a set of sample cases as the one I showed before, and the results has been presented to a cardiology specialist to assess whether the speed are safe for patients. Although the performance can be improved by taking into account the patient's physical fitness and lifestyle, the current results are completely safe and effective for all the patients. And thank you.
Teşekkür ederiz. Sorusu olan var mıydı acaba? Sorusu olan direkt mikrofonunu açıp sorabilir. Sanıyorum soru yok. Sunum için Yasmin Kehail'e teşekkür ediyoruz. O zaman bir sonraki sunum için Amna Khan, Automated Diagnosis of Chest Pathologies, Stroke Classification of Chest X-ray Using Deep Learning Architecture başlıklı sunum için Amna'yı davet ediyoruz. Evet. Açıldı değil mi Amna hocam?
Evet hocam.
Tamam, size bırakıyorum. Ben mikrofonu kapatıyorum.
Tamam hocam, teşekkür ederim. Good morning, everyone. Now, imagine that if computer could detect the pneumonia, heart failure, tumor, or any of the diseases just by looking at the X-rays. Like you take the X-ray images and the machine can diagnose the disease even before the doctor sees it. Today, we are gonna turn that idea into reality. So, for that purpose, I will represent my research on the automated diagnosis of chest pathologies through classification of chest X-ray using deep learning architecture. These are some of the main points that I'm going to discuss today. So, in order to understand this title, we should first understand why does this thing matter. So, you know that a radiologist spends over 13 years studying, training, reviewing thousands of medical imaging in order to master the art of reading the scans. It takes more than a decade of dedication, sleepless nights, and clinical intuition to build this over time. And all of this time, now imagine how much time a machine would take to learn all this. An AI model, it can be trained within few hours to a few days in order to learn all of this. So, can we not reduce all of that time and help the doctors achieve the medical understanding of medical imaging better? Not only will this be faster, not only this will help the doctors to diagnose the images faster, but will be helpful in the quicker treatments. Now, how is AI gonna learn from the medical imaging? For that to work, we have something called as convolution neural network. This is some sort of a pattern detector that is gonna detect the abnormalities from the images that we are gonna give it to. So we are gonna take the data set from the hospitals or from the internet, the online available data sets, and on basis of that data set, those medical images or AI is going to learn. So, there's a normal misconception that a number of people say they have this belief that AI, it's gonna replace the doctor. So is this thing true or not? So for this purpose, the AI is such a tool that is going to help doctors improve their jobs. For example, if a doctor is taking 10 hours daily, he's working on surgeries, he's seeing patients, and then he's also viewing images. because us humans, we have a limited capacity to work throughout the day. So the doctor is going to be very tired, and in order to diagnose those nodules or those cancer parts, it's very difficult. Whereas for the machine, it can work throughout the day and it won't be get tired. So the machine is not a competition. It's gonna help radiologists to do their job quickly and easily, and the doctor they can further see if the machine has classified the images in a good manner or not. So this is the dataset that is used for this purpose. This is an online available dataset that has more than 1,12,000 chest X-ray images with different sort of abnormalities present in it. This is like one of the biggest data sets that is available on the internet for doing classification, and we can apply deep learning on it, and it also has the labels available for all of those diseases, so the doctors, they can easily identify which disease is present. Now, AI can help the doctors to do their job, but how can AI help? There are some of the limitations that AI is facing in order to classify those medical images. So we are going to look into these details. So the main three key challenges that are being faced in order to classify those images is, first is the class imbalance, second is multitasking, and third is the data size. So in common language, if we say what is class imbalance means that when you see the medical data is like different from other fields data in a way that you see, for example, if there are 100 people, maybe one or two, they may have pneumonia, or if there are lots of people there, like within 1,000 people, one or two or maybe three people would get lung cancer. So the disease data is not something that's like very generalized. So it is like very few as compared to the normal data that is available. So this results in class imbalance. The second thing is multitask, because there is not only a single disease or two diseases present that are related to lungs. There are a large number of diseases that are present. So in order to tackle those large number of diseases, should we have different or separate algorithm in order to measure them? The third thing is dataset size. We do not, because we have like limited number of patients, so we do not have like larger dataset like in comparison to medicine. If we look at other fields, for example, surveillance and things like that, they have like millions of data sets available to them. But in case of medical imaging, the maximum you can get is 1,000 images, 2,000 images. So that is also a problem that is being faced. So how can these challenges be tackled? So for the first problem, that is class imbalance, what we can do is we can have the weight losses. What we can do is, if for example a disease have a smaller data set, we can give more weightage to that data as compared to the normal data. In that way it would be balanced, because if there is imbalance in class data, the algorithm is giving more weightage to the normal class as compared to the disease class, so it might miss some of the details that are related to the disease. In this way it may misclassify. That's why weight loss, it's like a very good option for us to use. The second option is resampling. What we can do is, for example, if we have 10 healthy patients and 4 patients who are diseased, so what we can do is from those 10 healthy people, we can take the data of 4 people and compare it with the data of 4 diseased people. In this way, by resampling, we can easily remove the class imbalance. The second thing is multitasking. For example, like at the same time, maybe there are different diseases present. A person may have pneumonia, and also maybe there's edema present. There is like he has like some early stages of cancer involved. So multiple diseases can be present. For that, if we design different algorithm for each disease, then it might be time taking, as well as it may consume more power to run those algorithms as well. So what we can do is we can use multiple labels for each of those diseases and combine them in one single algorithm and classify those diseases. The third thing is the dataset size. Because of the limited amount of data that is available to us, what we can do is we can have two approaches in order to overcome this problem. So the first one is called as learning. In transfer learning, what we do is we are gonna take a normal data set, for example, that is very natural. For example, we can take images of penguins or birds, and we can take that data and train all or algorithm on that data set. So like it can learn basic feature. For example, in order to determine an object from the background, and like color differentiation and basic things like that. And then we can retrain that, fine tune that model on our actual medical data set. So what it will do is on the basic layers, it will get the information it will take the information from the uh, general data that we gave, and then it will fine tune and the performance would be better. The second thing is data augmentation. What we can do is we can take the data and like move it, rotate it at different angles, the same data. And then what will happen is the algorithm, it will consider it as a new patient or a new person. So in this way, we can overcome these problems currently. So here you can see the thing that we talked about earlier, the class imbalance. Here it is shown in the first figure you see. There are different sort of diseases and all of them, they have different amount of data for each category. For example, here you see for hernia, there may be very small amount of patient because this condition would be not that common as compared to the infiltration one. So see, there's like a huge difference between the amount of data availability. And in the second photo, you can see the normal data as compared to the disease. The normal data is like a lot. So when the algorithm is going to train on this sort of thing, it will give more weightage to normal data and give very less weightage to the disease data because it's very less. In this way, we would have like it would train itself on features of normal data and it won't be useful to classify the disease. So in this way, what we are going to do, we are going to remove the class imbalance. When the class imbalance is removed, here the process that you're saying, this is weighed by changing the weights. By changing the weights, now we have equal amount of positive, negative for each of the disease. So it will give equal weightage to both of the diseases. In this way, this problem would be solved and then we can easily classify the disease. Now, for the classification model, DESNet is being used for classifying this sort of data. After classification, you know that we have results in the form of accuracy and confidence level. It would be 95% confidence level and 86% accuracy, things like that. But the problem with that is when when the problem is solved, the doctors, they cannot understand what the mathematical things are. They have to learn those things as well. So to create ease for the doctors, we have this thing called as class activation maps. Class activation maps, what they are going to do after they are going to use this data, do classification and like detect the diseases. After detecting diseases, it will give the colored images. From these colored images, the doctor can easily see, okay, these are the parts where there may be a disease, and each disease would have its own specific color. So instead of looking at all the images by themselves, they can use the algorithm, and from the algorithm, they can easily know, okay, these are the disease parts, and they will confirm in some cases where there may be a problem. So this is gonna create ease for the doctors and not replace them, but help them in order to improve the healthcare process. So this is a summary of all the points that we have discussed, how AI can help the diagnosis of chest X-rays and be applied in real life in hospitals. Thank you so much.
Teşekkür ederiz. Amna Khan'a sorunuz var mıydı acaba? Evet, değerli çalışması için teşekkür ederiz o zaman. Bir sonraki sunum için Oğulcan, Çelik, İbrahim Kaya ve Özlem Karabiber Cura'nın yazmış olduğu Recognition of Food Gestures Through Time Frequency Analysis and Deep Learning Techniques Using sEMG Data başlıklı sunum için konuşmacı olan,
Merhaba,
evet, Oğulcan Çelik sanırım konuşmacı. Oğulcan Çelik hocamızı davet ediyorum. Ben,
merhaba hocam. Ben
merhaba,
sunacağım. İngilizce olarak devam edeceğim uygunsa sizler için de.
ben mikrofonu kapatıp size teslim ediyorum ekranı.
Tamam, sağ olun. Hello, I'm Oğulcan Çelik. I will make my presentation as a Master Science student at İzmir Katip Çelebi University, Department of Biomedical Engineering. Before I start, I would like to thank my esteemed advisor and co-advisor, Assistant Professor Dr. İbrahim Kaya and Assistant Professor Dr. Özlem Karabiber Cura, respectively, for their supports. And I would like to thank Professor Dr. Mehmet Çevik about organization of this Congress. This presentation, I will share our research about a deep learning based approach for food movement recognition using time frequency analysis of single channel surface EMG signals. First of all, in our presentation, I will give a very brief information about EMG. Electromyography is extensively used to evaluate skeletal muscle electrically activity. Most existing approaches for recognizing food gestures really on manual extracted features from surface EMG recordings. Our study aims to develop a deep learning based method that automatically utilizes the time frequency representation of surface EMG signals from a single channel surface EMG, eliminating the need for manual feature extraction. To achieve this, a continuous wavelet transform is used to generate time frequency RGB images from surface EMG signals. Pre-trained deep networks, including Inception V3, Inception ResNet V2, and ResNet 18, ResNet 15, ResNet 101 were used for classification through transfer learning. Results show that the purpose method substantially improves surface EMG-based food gesture recognition. On the right-hand side of the slide, you can see one of the sample resting state images, RGB images we found in our research. Traditional food gestures classification with surface EMG often really on manual extraction, which is time consuming and inconsistent. Deep learning, especially convolutional neural network, enables automatic extraction of meaningful features from raw signals. Continuous wavelet transform and short time Fourier transform techniques supports advanced EMG analysis, aiding in multi-channel data acquisition and gesture recognition. Beginning of the collecting the raw EMG signal, first of all, we acquire raw EMG signals from the surface of the skin using electrodes. These signals reflect the electrical activity generated by muscle construction during foot movements. Pre-processing the raw signal is often noisy. So we apply pre-processing steps such as filtering to remove artifacts and baseline drift. This ensures that the signal quality is suitable for analysis. So after cleaning the signal, we extract meaningful features to represent it. These features can come from a time domain, frequency domain, or time frequency domain, as we use in our study, CWT and or STFT, which gives us both spectral and temporal information. Finally, the extracted features are combined into a feature vector. This feature is used as the input for classification models such as deep learning network. Part of the data collection and processing. First, we collected EMG signals from 12 healthy individuals performing 5 different foot gestures. Then we used continuous wavelet transform and short time Fourier transform to extract important time frequency features from the signals. Finally, we turned these into images and split them into 70% training and 30% testing sets to evaluate deep learning models. We purpose a novel method for classifying foot gestures using single-channel surface EMG signals, time frequency representation work generated using CWT and STFT, which were then converted into RGB images. As you can see illustration, the left hand column is STFT scalograms, RGB image, and the right hand column is CWT Morse scalogram RGB image. A and B resting state, C and D dorsiflexion, E and F foot inversion, G and H foot eversion, and I and J plantar flexion gestures RGB image. The reason we choose CWT more specifically is that is provided the highest accuracy during testing. As shown in the image, the Morse wavelet consistently outperformed others, giving us the best results for classifying the foot gestures. While performing the analysis, several model wavelets we used: Amor, Morse, Bump, Paul, and Morlet in continuous wavelet transform to capture unique EMG signal features and improve analysis robustness. Secondly, using the distinctive features of time frequency methods, SDFT provided a different time frequency perspective that complemented CWT insights by identifying transient features and frequency changes. With deep learning operations, models such as Inception V3 and Inception ResNet V2, ResNet 18, ResNet 15, and 101 were trained on spectrogram images to classify foot movements by optimizing accuracy. In our study, we analyzed how continuous wavelet transform wavelet parameters and the STFT method affect foot gesture recognition using deep learning models like deep learning networks applications. Continuous wavelet transform Morse with ResNet 101 achieved the highest accuracy of 78.9%. STFT with ResNet 80 gave the highest accuracy of 73.9%. These results emphasize the importance of selecting the right parameters and model for accurate biosignal processing. The Morse wavelet combined with ResNet 101 showed the potential for better performance, and swapping models as needed can improve results. The findings highlight how crucial it is to carefully choose both the parameters and deep learning models to improve accuracy in biosignal processing, especially for foot gesture recognition. The results suggest that using the Morse wavelet with ResNet 101 gives a notable advantage. In our experiments conducted with epoch between 20 and 2010, ResNet 101 achieved higher accuracy with Morse compared to other models. The table summarizes the performance of different transfer learning models, showing their accuracy rates. It provides a clear comparison of how each model performed in recognizing the foot gestures, helping us understand the strength of each approaches. As can be seen in the visual data on the left, ResNet 101 was found to achieve over 83% classification accuracy for resting, dorsiflexion, and plantar flexion movements using continuous wavelet Morse images. With these results, the ROC AUC values exceeded 87.23%, confirming the robustness of the continuous wavelet transform Morse method for all foot movements. As a conclusion, The surface EMG food data analysis showed consistent results with Morse wavelet and ResNet 101 achieving the highest accuracy of 78.9% and more, and bump parameters with Inception V3 reach 73.9% accuracy. Morlet performed poorly with ResNet 50, scoring 44.4%. Powell and STFT methods recording 66.1% and 73.9% accuracy respectively. These results highlights the importance of selecting the right parameters and models with feature work, focusing on optimization and transfer learnings. In the future, studies will focus on expanding the data set and increasing the number of surface EMG recording channels to capture more detailed muscle activity, improving classification accuracy. The goal is to enhance the interpretation of surface EMG signals for health technologies. This research aims to advance clinical diagnostics, rehabilitation systems, and intelligent prosthetics by integrating improved surface EMG analysis methods. Thank you for your listening.
Teşekkür ederiz sunum için.
Ben teşekkür
Sorunuz
ederim.
var mıydı acaba? Oğulcan Çelik'te. Sorusu olan yok sanıyorum. Çok teşekkür ederiz
Teşekkürler.
çalışmanız için ve emeğinize de.
Teşekkürler.
O zaman ben bir sonraki sunum için Fouad Zahran, Zeinab Zahran, Farah Mekawy, Moamen Elbahnasy ve Abdallah tarafından yapılmış olan Sustainable Synthesis and Characterization of Nano-Hydroxyapatite from Chicken Bone Waste for Biomedical Dental Applications başlıklı sunum için davet edeceğim ama sanıyorum girecek olan Zeinab Mokhtar. Doğru mu? Evet. Merhaba, orada mısınız? Orada mısınız acaba Zeinab?
Merhaba Musra. Noureldin Abdallah.
İki kişi açtı ama aynı anda sunumu sunacak olan kimdi acaba?
Evet, we are two persons. Noureldin Abdallah will start
Tamam.
now.
Okey. Ben mikrofonu kapatıyorum. Size bırakıyorum.
Tamam Musra.
Hi everyone. My name is Noureldin Abdallah, and our team is Zeinab Mukhtar and Farah Khamis and Moamen Hassan. We are senior students of Biotechnology Department, Faculty of Science, Helwan University in Cairo, Egypt. Our project today titled is Sustainable Synthesis and Characterization of Nano-Hydroxyapatite. Our mission is can we protect both our health and our environment in the same time? This simple question sparked a journey that led us from two major problems to one powerful solution. Let us take you through how we thought and we researched. First, dental health and toothpaste chemical in Egypt and in global overview. Let's begin with the first issue, oral health. Globally, over 3.5 billion people suffers from oral diseases. 3 of 4 people is suffering is in developing countries. With tooth decay being the world most common health condition, and in Egypt the number is alarming. 70% of adults have untreated dental caries. Around 60% of children suffer from cavities. Now, here is the catch with the fluoride in toothpaste. Helps fight cavities. Too much fluoride can actually damage the teeth. In Egypt, some toothpaste brands contain high fluoride levels, which raise the serious concerns about long-term safety. So, we ask ourselves, is there a savior natural alternative work just as well? Other problem is the solid animal waste. While exploring the question, we came across another serious challenge: animal waste, especially poultry bones. Every year, millions of tons of animal byproducts are generated globally in developing countries. Poor disposable methods lead to harmful gas emissions and environment degradation. According to the FAO, over 25 to 30% of slaughtered animal mass become unmanaged waste. In Egypt, thousands of tons of poultry waste are discarded yearly due to the lack of centralized treatment. This leads to open air decomposition, cause air pollution, and uncontrolled methane emission, which damage the local climate conditions. This made us wonder, what if this waste wasn't just waste? What if it could be turned into something valuable? And that's where our innovation come to life. We didn't just want to treat our health problem, we wanted to redefine how approach them. So we looked at one of the Egypt's most overlooked waste streams, poultry ponds. What if this waste could do more than pollute the environment? What if it could actually protect our smile? We developed a process to transform chicken bones into nano-hydroxyapatite, a naturally derived biocompatible material that closely mimics the material structure of human health. It's already used in high-end dental products, but we found a sustainable and low-cost source, poultry waste. We then formed a toothpaste enriched with the nano-hydroxyapatite, resulting in a product that is sustainable, using recycled animal waste instead of synthetic chemical, safe and fluoride-free, ideal for children and adults alike, effective, promoting annual harmonization and cavity prevention, and eco-friendly, reducing the environment impact of the poultry industry. Through this solution, we tracked three problems at once: oral health risk, environment pollution, and industrial waste. And how we can manage this and our experiments, Zeinab Mukhtar will explain it more.
As Noor explained, that our application depends on extraction of nano-hydroxyapatite from chicken bone, especially from femur bone. I want to explain why femur. The femur bone contains high concentration of hydroxyapatite than many sources of hydroxyapatite. Now for methodology. Our project divided for three steps. First, preparation. That was made of bone collection and applied different treatments such as grinding, drying, and calcination on our bones. At this point, we went through the second stage, that was characterization. This stage made us confident that we had nanoform from hydroxyapatite and has a structure that gives us high activity, which we made different tests to be ensured, such as synthesizer for ensuring nanoscale, FTIR to ensuring that essential components of hydroxyapatite are present, and finally SEM to show surface morphology, which was fibrous structure that let us have high surface area and high activity. Then we went through final stage, which was application stage. Here we add our material in toothpaste form uh, as alternative to toxic fluoride and make our first prototype. So
Evet, teşekkür ederiz. Zeynep Muhtar'a sorusu olan var mıydı acaba? Bir sonraki sunuma geçeceğim. Zeynep Muhtar ve iki kişi sundular Abdallah'la birlikte. Teşekkür ediyoruz. Bir sonraki sunum için Muhammed adım Hüseyin. Burada hibrit genetik and greedy algorithm based RSU deployment for enhanced connectivity in vehicular networks başlıklı sunumu için.
Okay. Merhabalar, sesim geliyor mu?
Evet, geliyor. Ben mikrofonu kapatıyorum, şu an sizi dinliyoruz.
Tamam, ben ekranı paylaşıyorum. Hocam orada ekran paylaştım da çekiyor mu?
Evet, görebiliyoruz.
Tamamdır. Burada ben Muhammed Çatlıyım. Bugün hibrit genetik ve grid algoritm bazlı bir arayüzü deployment and forensic connectivity in Vehicular network'tan bahsedeceğim. Bizim akışımız bu şekilde olacak. VANET'ten bahsedeceğiz. Yani araç tasarısız ağların nedir? Onun uygulamaları, bağlantı yönlendirme protokolleri, güvenlik, ilgili çalışmalardan bahsedeceğiz. Daha sonra genetik ve ağaç göçlü algoritmadan bahsedeceğiz. Uygulama ortamları, birkaç tane örnek ve sonuç ve öneriden bahsedeceğiz. VANET nedir? İşte VANET teknolojisi günümüzde insanların hayatlarına en etkileyici bir ve kolaylaştırıcı bir teknoloji haline gelmiştir. Bilindiği üzere vanetlerin yani araç tasarısız ağların araçtan araca ve araçtan yani yakındaki olan araçların birbirlerine iletişim sağlayabilmesi ve araçtan altyapıya iletişim sağlayabilmesi bir ağ türüdür. Yani geliştirilmiş bir ağ türüdür. Bu araç tasarısız ağların başta trafik akışını düzenlenmesi, trafik kazaların anlık müdahale edebilmesi veya acil durumlarda kritik bölgelerden bilgi toplanması yönelik bir işlev yerine getirebilmek için geliştirilmiş bir ağdır. Onların büyük avantajları mevcut ağların yani altyapısına ihtiyaç duymaksızın olağanüstü durumlarda alternatif bir iletişime aracı olarak kullanabilmektedir. İşte onların altyapıdan yani vanet altyapıdan araca, araçtan altyapıya bir iletişim sağlayabilmektedir. Bu akıllı ulaşım sistemleri araçların yolcu bölmesindeki altyapılar ve araç içi terminal gerçek zamanlı bir bağlantıya açılır ve kullanıcının bilgiye doğrudan ve hızlı bir şekilde erişmesini sağlar. Yani o mobil tasarısız ağlardan en büyük farkı hareketliliğinden oluşmaktadır. Bir örnek görecek olursak bu şekilde yani görüldüğü üzere burada bir yol kenarı yani arayüzü veya merkezi yetki birimi yönetmen şeysinden onların birbirlerine arayüzlerin birbirlerine kablo ile bağlanabilir veya internet üzerinde bir bağlantı sağlanabilir. hatta V2V yani araçların birbirlerine bir iletişim sağlanabilmektedir. Veya aracın ve altyapıya bir iletişim yani V2I sağlayabilmektedir. İkinci örnekte görecek olursak bu şekilde daha çok görünülebilir. İşte araçtan araca bir iletişim gösterilmektedir burada. Ve hatta araçtan arayışıya iletişim gösterilmektedir. Onların birbirlerine kablo ile bağlanabilir ve daha sonra ise internet üzerinden de arayışların birbirlerine bağlanması mümkündür. İşte aynı şekilde mesela onun arayışının kapsam yerine bu şekilde mesela kapsadığı yer bu şekilde. Onların yerleştirilmesi çok bir maliyet olacağından işte bu çalışmaya döküldük. Ben daha hızlı biraz geçeyim ki vakit çok olmasın. İşte bağlantı ve yönlendirme protokollerinden bahsedecek olursak araçların yoğunluğun artmasından her zaman daha yüksek bir bağlantı ile sonuçlanmayabileceğini araç yoğunluğunun ve yol konfigürasyonunun minimum iletim menzilli değeri üzerindeki etkisidir. İşte bu yönlendirme protokollerin niye amaçlı kullanabilmektedir? İşte bu temel amacı minimum miktarda ağ kaynağı kullanırken minimum iletişim süresi elde etmektedir. Ve bilindiği üzere vanetlerin yönlendirme protokolü bu şekilde topology based, position based, geocast ve broadcast and son olarak cluster based topolojisi olarak görülmektedir. Yol kenarı ünitesi veya roadside unit'ten bahsedecek olursak işte bu şekilde görselde gösterildiği gibi onların önemli
Ses gitti ama sesiniz şu an gelmiyor. Muhammed biz biliyor musunuz?
rollerinden bir tanesi
Şimdi
bilgilerin
sesiniz
araca
tekrar geri geldi.
iletilmesi.
Sesiniz gitmişti, tekrar şimdi sesiniz geri geldi. Tamam, teşekkürler.
Hocam kusura bakmayın sesim kesildi de hocam geldi mi acaba?
Şimdi geldi şu anda. Tamam, buyurun.
Arama geldi ondan kusura bakmayın hocam. Evet, güvenlik gereksinimleri bu şekilde mesela güvenlik, verimlilik ve izlenebilirlik çok önemli olduğum için ondan bahsetmek istedim. Bu alanda ilgili çalışmalar çok olduğu için ben genel olarak önemli olan çalışmaları buraya naklettim. Genelde bu çalışmalarda aerosuların yerleştirilmesi sorunu uygulamaya bağlı olduğu sonuca varabiliriz. Mesela birçok araştırmacının en iyi arayüzü konumları kentsel senaryolarda yani kavşakları ve otoyol senaryolarda ise tek tip dağıtımı kullanmayı tercih etmişler. Bizim burada sorun bildirimi dinamik trafik desenleri arayüzü yerleşmesini zorluyor. Bütçe ve ölçeklenebilirlik kısıtmaları da çok önemli. Kapsam, gecikme ve maliyet arasında da bir denge ihtiyaç olduğunu görülmektedir. Bu çalışmamızda ise yani verilen harita düzeninde arayüzlerin uygun ve optimal şekilde yerleştirilmesi sağlayan genetik algoritma ve açgözlülüğü dayalı önerdik. Çalışma amacı ise aşağıdaki kullanılarak hibrit bir optimizasyon geliştirmek. Açgözlülüğü algoritma yani bütün bu açgözlülüğü ve genetik algoritma kullanmak amacımız hedef veya amacımız maliyet ve gecikme en aza indirmekti. Genetik algoritmamız bu şekilde çalışmaktadır. Yani onun önemli aşamaları başlatma, seçim, çaprazlama, mutasyon Onun gücü mesela küresel aramasında bu şekilde mesela başlangıç popülasyon, daha sonra bireylerin değerlendirilmesi, yakınlama, eğer yakınsamanda ise evet dediyse en iyi çözümü bulunmaktadır. Hayırsa seçim devam edecek. Mutasyon ve çaprazlama, daha sonra ise tekrar yakınsama gelecek. Bu şekilde devam edecek. Gözlü genetik algoritma sonrasından uygulandı. En iyi performans gösteren düğümleri hızla seçer. Onun güçlü yönü yerel optimizasyonu elde etmektedir. İşte bizim gözlü algoritmamız önemli adımları bu şekilde. Öncelikle SIMO yardımıyla bir ağ oluşturulması, daha sonra ise ağ grafiği olarak dönüştürülmesi, algoritma ağ üzerinde geliştirilmiş, düğümlerin kenar sayılarına veya derecelerine göre büyükten küçüğe doğru sağlanması, dağıtılacak arayüzlerin sayısı sabit olarak belirlenmesi, daha sonra ise sıralanan düğümlerde eğer dağıtılacak arayüz sayısına sıfıra eşitse döngüden çıkış, değilse arama devam edecek. Arayüz kaplama alanı hesaplanacak. Dağıtılacak arayüzlerin koordinat bilgisinin alınması ve arayüzlerin sayısına ulaşana kadar dağıtım sağlanması ve daha sonra ise dağıtılacak arayüzlerin kalmadığında algoritma otomatik olarak sonlanır. Almış olduğumuz örneklerde arayüz sayısı, kapsadığı düğüm sayısı ve algoritma çalıştırma süresi bu şekilde. Bir aldığımızda 4 tane düğüm kapsamıştı. Ve algoritma çalıştırma süresi 552 idi. Bu şekilde devam etmiştik. Yani genetik algoritma çözüm alanını araştırır, gözlü en iyi adayları ince ayarlar. Arayüzü dağıtım için kullanılan gözlü algoritması ağdaki en yüksek dereceye sahip olan düğümleri seçen ve sabit sayıda arayüzlerin yerleştiren basit bir yaklaşımdır. Öte yandan arayüzü dağıtımı için genetik algoritma daha iyi çözümler bulmak için popülasyon tabanlı bir arama stratejisi kullanılan daha sofistike bir yaklaşımdır. Sonuçlar, yani gecikmede çok iyi bir azalma olduğu gösterilmektedir. Kapsamında da iyileşme olmuştur. Altyapı maliyetinde de bir düşüş gösterilmiştir. Yani kentsel ve yarı kentsel alanlarda da etkili olduğunu görülmüştür. Gözlü algoritma daha hızlı ve basit olmakla birlikte problemin tüm örnekleri için en uygun çözümü olmayabilir. Onun için genetik algoritma ise daha karmaşık bir yaklaşım ve daha fazla hesaplama kaynağı ve zaman gerektirebilir. Ancak daha fazla optimum çözüm bulma potansiyeli sahiptir. Bizim uygulama ortamlarımız mesela çalışma için birkaç temel simülasyon ortamı sağladık. Bunlar burada saymayacağım. Görselde gösterildiği gibi. İşte OpenStreetMap'ten harita aldık. O almış olduğumuz haritayı, yani gerçek haritayı GAT.com ile öncelikle convert ettik. Daha sonra ise network'e ulaştırdık. Ondan sonrasında GAT.com ile zaten ağın nasıl olduğunu gösterilir. Daha sonra ise Tracy aracıyla SIMO'da aynı şekilde bir simülasyon gerçekleştirdik. Ondan sonra ise analiz içinde de Omnet kullanmıştık. Evet, fitness'i bu şekilde arayüz sayılarına 14 aldığımızda, yani görüldüğü üzere fitness'i bu şekilde gösterilmektedir. Mesela burada en iyi olduğu bölgelerde mesela 8'ten 12'ye kadar, 11'e kadar en iyi performans gösterdiği şeylerde ve selection ratio'da da aynı şekilde fitness ile birlikte bu şekilde göstermektedir. Sonuç olarak araç tasarısız ağların kullanımını gün geçtikçe çok artmaktadır. Araçların kendi aralarına ve yol kenarlarındaki yol kenarı birimleri ile haberleşmesini sağlayan yapı, e, yol güvenliği, araçların daha güvenli bir şekilde yol alması sağlamak, trafikte herhangi bir kaza ya da sıkışıklık olduğu zaman diğer araçlara haber gönderen, daha güvenli bir yolculuk yapmasını sağlayabilir. Araç tasarısız ağlarında yol kenarı birimi yüksek maliyeti olduğu için en optimal şekilde konuşlandırılması veya yerleştirilmesi gerekmektedir. Bu çalışmamızda genetik algoritma ve aç gözlü algoritma ile optimize edilmiş şekilde arayüzlerin en uygun konuma yerleştirilmesi hedeflenmiştir. Yani bu araç ağlarında etkin şekilde gelecek günlerde çok kullanabilmesi, olası saldırılara karşı korunması olmasına bağlıdır. Araç ortamına yapılacak saldırıların ilerleyen zamanlarda giderek artması beklenmektedir. Beni dinlediğiniz için çok çok teşekkür ederim. Biraz şey oldu.
Biz teşekkür ederiz emeğiniz için ve sunumunuz için. Muhammed adım hissini sorusu olan var mı?
Evet o hani. Efendim hocam duyamadım.
Sorusu olan var mı diye sormuştum.
Ya, tamam.
Ekibimizde sorusu olan yok görünüyor. Tekrar emeğinize teşekkür ederiz. O zaman
Teşekkür ederim hocam.
bir sonraki sunum için Raja Tafkan, Zekeriya Tüfekçi
Tamam.
hazırladığı The Impact of Word Embedding Technique Use on Machine Learning Classifiers for Sentiment Analysis in Low Research Language In-Depth Study of Ordi sunumu için davet edeceğiz. Kim katılacak sunuma diye bakıyorum şu anda.
Teşekkür ederim hocam. Am I audible?
Raja,
Yes.
tamam. Tamam,
Okay.
Raja olarak görünmüyor. Aftap olarak görünüyor şu an isminiz. O yüzden karıştırdım. Tamam, o zaman ben size tekrar mikrofonu size bırakıyorum. Ama siz mikrofonu kapatabilirsiniz. Teşekkür ederiz. O zaman
Tamam.
Aftap Nasien, sizde sunum sırası. Dinliyoruz. Ben mikrofonu kapattım.
Teşekkür ederim hocam. My name is Aftab Nasim. I'm from Cura University, pursuing my doctoral study. First, I would like to thank the chair and the organizing committee of this conference. And my topic is the impact of word embedding techniques on machine learning classifier for sentiment analysis in low resource languages, the study of Urdu. Okay. First of all, we'll start with the sentiment analysis. The technology is constantly evolving for better understanding the behavior, including the sentiment expression and insights. The social media platforms generate a massive amount of data that need to be analyzed for the sentiments. And the artificial intelligence and the computers that need to anticipate and judge the sentiment to evaluate your human needs. Basically, the sentiment analysis is the use of natural language processing, computational analysis, and linguistics to determine the sentiment. To determine the overall sentiment expressed in a piece of text, such as a social media post or a review or a headline for a news or any email or any other thing. The computational studies of opinion, sentiments, and emotions, they are like in case of when we study this thing, what we do is we basically divide them into like sentiment levels or a document level or on the aspect levels. For sentiment analysis, basically, there are three types of techniques that are used, three different approaches. The first one is the lexicon-based approach that is based on the sentiment lexicon that are present in a statement that are associated as a positive or a negative or a neutral gesture. Then the other approach that is most common now is the use of machine learning, deep learning based are the language models also. These kind of algorithms to automatically classify the sentiments from the textual data. And another approach is the hybrid approach that combines the lexical based approach, that is the dictionary based basically, and those of the machine or deep learning techniques. So why Urdu? Urdu is a kind of language, like it is the most widely spoken language in the Southern Asia, South Asia, specifically in Pakistan, in a part of India and other part of the world. There are more than 230 million users. it's a variety. It has a variety of contents that is created for Urdu in the textual form and is available on the social media and the web. So Urdu is considered as resource deprived for natural language processing, specifically because the problem is, first of all, it has a rich morphology and it has a complex script. Its script is more like Arabic. And then the less number of annotated corporas are available for the sentiment analysis. And also there are few pre-processing libraries that are present for NLP job as compared to the other languages like English, German, Chinese, etc. And also for Urdu, actually it is written as Urdu text, and then as a Roman Urdu. We call it like we write in English, but we write Urdu but in English alphabets, and also we are using English. So it's a kind of a code switching. And then it has a context dependent semantics. Our objective for this work is to analyze the role of the word embedding, word representation in enhancing machine learning classification accuracy to predict the correct sentiments. And also another thing is to judge the quality of the word embeddings generated through the traditional embedding methods and the large language models in enhancing the machine learning classifiers accuracy. That is a few glimpses of research, the previous research. We can see that many peoples have done the research with a variety of data sets and variety of models. When we go to the material and methods, like first of all, we start with the data processing, because the data, wherever the data is collected from in a form of a data set, it is in a raw form. So that need to be processed before giving it to any algorithm or any processing mechanism. So we need to convert it to a lowercase, remove the punctuation marks, special character, URL, symbols, numbers, the language, other language words, and then we need to change the abbreviations to their full forms. And also there is something like we call it stop words. That is a small library. For our case, like we use like 260 words that are most commonly used in language to construct the sentences, but they doesn't carry any emotion or any sentiment value. So we just remove those words from the sentences just to lessen the burden. Then after that, the tokenization is applied to split the sentences into a list of single words. Like every word is one token for computational purpose. Then further lemmatization is used. It's a technique that used to standardize the words. Like if a word that is used in its many forms, it's available in many forms. Like any word that is having 2 or 3 their variations, but we just convert it to a base word. The word embedding techniques to make the words interpretable by machine learning and deep learning, they must be represented numerically. So for NLP techniques, the things that we are using here is word2vec and fast text. These are two traditional word embedding techniques, and then we are generating the word embedding that are based on the large language models. That is a sketch of the thing. If you see the embeddings, we can distribute into 3 major types. The traditional embeddings like bag of words, term frequency, and the co-occurrence matrix that are used with machine learning previously. Then comes the static word embeddings like the word2vec, globe, fast text. These techniques are very, very popular, and they are used mostly with the deep learning algorithms, and they provide excellent embeddings. And recently we come across the BERT models and a variety of these large language models, bidirectional encoders. So they are also used to generate the contextualized embeddings, and that are also enhancing the accuracies of the systems. So the first if we see the word2vec, it's a kind of it maps the word to a high dimensional dense vector representation to capture the semantic relationship between the words. It has a tendency that the words with the similar meanings, they should have a similar vector representation. It captures information about the meaning of the word based on the surrounding words. Word2vec algorithm estimates representation by modeling text from a large corpus of the data. It has some drawbacks also, like if you train your model from a large corpus, but if you give it certain text that is not available in that corpus, that we call it out of vocabulary, so it struggles to generate embeddings for that. And also it usually generates static embedding. That means it doesn't consider the context of the word that is used in a sentence. It has two major types, that the continuous bag of words and the skipgram. These are the architectural model, that how they work. They use deep learning to learn the target words for those techniques. I'm not going to discuss this here. These are this model for continuous bag of words and skipgram. Here is a bit easy representation. For example, we see the words that are represented in a form of vectors of multiple dimensions. Usually we use a dimension of 300, like each word is represented a vector representation of 300 numerics. So once these numerics are created, then you can visualize them in a two-dimensional space. For example, here you can see, and interestingly, for the normal text, you cannot actually subtract or add or anything, but with these embeddings, actually each word is represented in a form of a numerics. So basically, when you use such kind of things, like for example, we see that the similar context, they appear to closer to each other, like men, women, king, queen, their vectors are related to each other. So if we add a man's vector and then subtract from woman's vector and adds a king's vector from the king, will get a vector that is very close to the vector representation of the queen. So this is how it works. And then another embedding technique, that is fast text, that is an enhancement of the word2vec, and it uses some word information like the character engrams to handle rare or misspelled word. Basically what it does, it takes the word and then it convert it to engrams, like for example, apple for first three digits, then second three digit, then the third. So this way, sometime it is actually great for morphologically rich languages like Turkish, where a certain word has a lot of components within the single word, and then it handles out of vocabulary words better, because it breaks down the words into different parts. But it is actually complex to train and slower than word2vec. Then comes to the language model. We generate contextualized embeddings, word embeddings, through large language models. These embeddings are the semantics backbone of the large language models. Basically, what we generate is the deep contextual embeddings from the transformers. We use dense vector representation from the models like BERT, multilingual BERTs, distal BERT, Roberta, cross-lingual Roberta, RAMBERT, mini-LM, to capture the semantic and contextual information. And it highlights the popular models. Like, coming to the advantages, the contextual embedding is superior in terms from the regular embeddings like word2vec, fast text, or even bag of words and TF-IDF. And it leverages pre-trained knowledge from for downstream task, because the model is already trained on a large corpus of the data. And it comes with the rich semantics. The embeddings encode syntactic, semantic, and relational structures. But on the other hand, it has a certain constraint that you cannot train your model without the help of a GPU. The GPU is a must, and these models are really memory intensive because they use a lot of RAM. So, but they are able to generate the context. For example, there is an example for it's a word teak, that means it's right actually in English. So there are two sentences. These sentences is like wo bahut theek hai. This means is he is very right, and ye theek karna, this means is this thing need to be fixed. Now here the word theek comes in two sentences, but it carries a different semantics, different meanings as context to the sentence. So the bird handles these things effectively. Then we use machine learning classifiers and then we are using some of the prominent models for that. Okay. And then lastly, evaluation of these models are created through we use standard accuracy measures like accuracy, F-score, precision, and recall. The data set, basically for this study, we used 4 different data sets. The two are created by during my study. Actually, they contained news headlines. Basically, there are balanced data set of positive and negative news samples with 26,000. One data set contains around 26,000 samples and the other contains 31,000 samples. And there is publicly available Kaggle available data set from Kaggle that has 50,000 samples. This is also a balanced data set, and third data set is a small data set that is also balanced, but it has Urdu news headlines and some text. The proposed model is like the data is passed through this data processing mechanism. There the data is cleaned, normalized, tokenized, stop words are removed, and they are converted to their base forms, and that data is then fed to embeddings like word2vec or fast text to generate embeddings. Those embeddings are then fed to the machine learning classifiers to generate the sentiments. And for the large language model, it has a liberty that it has its own tokenizers. So we don't need to actually pre-process the data. We simply fed the data to a language model, and then it automatically it process and it generates the embeddings, and those embeddings are then fed to the machine learning like the earlier case. So for that embeddings, basically we use two kind of things. For example, for word2vec and fast text, there are two kind of models. One are the pre-trained models that are already available, and then there are the models that we discussed earlier that we trained from our data from those stats. So let me explain from the graph. When we applied those graphs, we says that the fast text model, that is the trained version of the fast text, it provides better accuracy for almost for all classifiers. It's nearly around 84%. And then the other models, they also processed well, like the word2vec pre-trained model also perform better, but not as compared to the first one. The same happens because we have the 4 data sets. So I'm explaining from the graph. The other data set, the same thing happens that like the fast text trained model, it performed exceptionally well. And then the other models, they are far behind from that context. And then we goes to the third data set, that's a bigger data set. And here we can also see that here the fast text trained model also performed exceptionally well. And then there is the word2vec trained model with the skip gram version and the continuous bag of word. It also tried to tried a closer margin. And then lastly, with a smaller data set, when we apply this thing here, the fast track trained model keeps its superiority, and the other models they perform averagely as compared to the first one. But the few ones they are the trained versions, but they the word2vec trained versions they underperform because the lack of data and they couldn't conceptualize the embeddings. So the fast track trained embeddings outperformed all other embedding methods due to its ability to cater out of vocabulary words, And then the word-to-vec pre-trained embeddings shows promising results. And we can say that the trained word-to-vec models, they underperform except for a larger data set. In terms of models, classifiers, the random forest and the boosting classifier, it performed exceptionally well. Then the logistic regression and SPM also shows good performance, but naive Bayes and decision trees slightly underperform. Then comes to the results from this large language model. Let me explain something. This because it's a complex result. On the left side, you can see there are 27 different variants of the LLMs that we use. That is ranging from the BERT, then the multilingual BERTs, digital BERTs, Roberta-based models, cross-lingual Roberta, GPT, then mini LM, RAMBERT, etc. We'll explain this result from this graph. As you can see this from this graph, they achieved a very good accuracy about for example, the multilingual BERT with that is actually fine-tuned with Urdu data that performed exceptionally well with about 90% accuracy, and also cross-lingual models, Roberta models, they performed with it about 85%, more than 85% accuracy. So we have tried with all the data sets, like you can see, but this pattern follows. Like for every result, we can see that cross-lingual Roberta and this multilingual BERT that is fine-tuned for Urdu, they performed better for every case. So the same happens with all the models. Like this means that our model is working perfectly because we tried with a variety of data sets. So whether they are small, and with this is the last one, the same thing approaches, like we have a good accuracy. So here we can say that the BERT variants dominate with a fine-tuned multilingual BERT that is achieving highest accuracy, that is greater than 93% in some data set and 90% in the one. It's likely to capture the structures of the language and contextualized ambiguities that is unique to the Urdu. The other cross-lingual models also achieved exceptional performance due to this task-specific optimization of the Urdu and demonstrating the strength of multilingual. DBERTA and RAMBERT, they are also the variants of the BERT models. They also demonstrated strong performances. But the catch is that they are computationally expensive models because they require a lot of GPU. The analysis demonstrates that the choice of the word embeddings in the classifier significantly impacts the sentiment analysis performance on the Urdu text. For example, here we can say that the fast text trained embeddings combined with ensemble classifiers like random forest and the boosting methods, they achieved state-of-art results. And the pre-trained word-to-vec models offer also a balance between the performance and resource requirement. In terms of language model, the fine-tuned multilingual BERT variants with Urdu-specific cross-lingual Roberta models, and then the DBERTA and RAMBERT language models from the BERT, they performed exceptional, they achieved exceptional accuracies and proven out to be very effective. These findings provide actionable insights for NLP practitioners working with Urdu or other languages to underscore and need language-specific embedding strategies in low resourcing contexts. In future, we are going to enhance this thing with the deep learning methods, and also for the language models that need to be expressed with other variants of the language models, and also with parameter optimization techniques. Thank you very much.
Teşekkür ederiz. Aftap, Nasim'e sorusu olan var mıydı? Emeğinize
Sorry.
sağlık. Güzel bir çalışma olmuş. Buyurun.
Tamam.
Sorusu olan var mıydı? Evet, tüm çalışmalar çok başarılı ve gerçekten çok emek verilmiş çalışmalar. Herkesi tebrik ediyorum. O zaman oturumumuzu burada sonlandırıyoruz. Bir sonraki oturuma kadar da ara vereceğiz. Tekrar çok memnun oldum tüm hocalarıma. Teşekkür ediyorum ben de. Herkese iyi çalışmalar diliyorum.
Teşekkürler, iyi çalışmalar.
Çalışmalar, hoşça kalın.
Hocam kamera açabilirsek bir resim alalım. Buradaki arkadaşlar, müsait olanlar. Teşekkür ederim.
Teşekkürler.
Furkan Bey, duyabiliyorsanız oturumu e, nasıl devam ettirebiliyor muyuz? Yani katılım belgeleri olmayacak bu şekilde değil mi?
Katılım belgeleri yok hocam.
O
Onları
zaman,
daha sonra da göndereceğiz.
o zaman oturumu terk edebiliyoruz herhalde şu anda.
Evet hocam.
Tamam,
Bittiyse
tamam. Çok teşekkür ederim. İyi çalışmalar diliyorum herkese.